Picture the moment before takeoff. You are buckled into a seat. Around you, maybe 250 other people are doing the same thing, stuffing bags into overhead bins, adjusting headphones, staring at phones. Nobody is thinking very hard about what is about to happen. And what is about to happen is genuinely astonishing. A machine weighing somewhere between 150,000 and 900,000 pounds, depending on the aircraft, that's the combined weight of a small apartment building, is going to accelerate down a strip of concrete and then just leave the ground. And then it is going to stay off the ground for hours at 35,000 feet with you inside it. There is nothing beneath you but air, not a platform, not a net, not a tether. 6 miles of open air between your seat and the earth. And the thing preventing you from becoming a very fast-moving piece of debris is a curved sheet of aluminum doing something to the air around it. You would think, given that roughly 100,000 commercial flights take off every single day, that this is a phenomenon humanity has thoroughly figured out and clearly explained. And in terms of the physics, yes, we have it. We understand it well. We can calculate it, simulate it, design billion-dollar aircraft around it. But if you actually ask someone to explain it, a physics teacher, an engineer, a pilot, someone at a dinner party who just watched a documentary, you will almost certainly get an explanation that is completely, fundamentally, and demonstrably wrong. Not approximately wrong, not a simplification that leaves out some details. Wrong in the same way that saying the sun orbits the earth is wrong. Confidently wrong. Textbook wrong. Wrong in a way that has been reproduced in classrooms for generations. So let's fix that. But first, let's do the polite thing and actually listen to the wrong explanation, because it has survived this long for a reason. Here is the explanation. You have heard it, perhaps you believe it. A wing is not flat on both sides. The top surface is curved. It arches upward in the middle and curves back down to the trailing edge. The bottom surface is much flatter. This means the path over the top of the wing is longer than the path underneath it. Now, when the wing slices through the air, it splits the oncoming airflow at the leading edge. Some air goes over, some goes under. Here is the key claim. Those two parcels of air, the one that went over and the one that went under, must arrive at the trailing edge simultaneously. They parted at the same moment, so they must reunite at the same moment. Since the air on top has a longer distance to cover in the same amount of time, it must travel faster. Daniel Bernoulli, the Swiss mathematician, showed that in a moving fluid, regions of higher speed correspond to regions of lower pressure. Faster air means lower pressure, so the top of the wing has lower pressure than the bottom. That pressure difference pushes the wing upward. That upward push is lift. It is elegant. Every step seems naturally to the next. Curved wing, longer path, faster air, lower pressure, lift. You can draw it on a napkin. It feels satisfying in the way a good proof feels satisfying, like there is no other way it could be. And that feeling of inevitability is precisely the problem, because the most seductive wrong answers are the ones that feel airtight. Let's actually test this. Let me show you exactly where this explanation collapses, and I want to be systematic about it, because there are not one, but 4 entirely independent ways it fails. Problem 1. The first premise has no foundation. The whole machine runs on a single pin, the claim that the two parcels of air must arrive at the trailing edge simultaneously. Equal transit time, call it that. Now ask yourself, what law of physics requires this? What equation derived from first principles predicts this outcome? Take your time. Look through Newton's laws, look through the work of Euler, Bernoulli, Navier-Stokes, anyone. There is no such law, no reason, no equation, no derivation, no principle that says two masses of air that separate at the front of a wing are obligated to meet again at the back. The premise is an assumption. It was never proven because it cannot be proven because it is not true. Someone thought it sounded intuitive and wrote it down. Then it got copied, then it got copied again, and now it's in textbooks.
Pull out this one assumption and the entire chain of reasoning falls apart before it even begins. Problem 2. The numbers are embarrassingly wrong. Let's say you're feeling charitable and you think, fine, maybe it's not a strict law, but maybe it's approximately true in practice. After all, lots of things in nature find equilibrium without being forced. Smoke tunnel experiments and computational fluid simulations destroy this hope completely. When researchers track where the air actually ends up, what they find is not a gentle deviation from the equal transit prediction. The air traveling over the top of a real wing arrives at the trailing edge dramatically, laughably earlier than its counterpart from the bottom. The two parcels are nowhere near each other. The velocity of air over the top of a real wing is far higher than equal transit time would ever predict, often 2 to 3 times higher than what the theory requires. Not a rounding error, a factor of magnitude. Problem 3 is symmetric wings generate lift. If longer path on top creates lift, then a wing with the same curvature on both surfaces, a symmetric aerofoil, the same shape on top and bottom, the same path length on both sides, should produce exactly 0 lift, according to this theory. No path length difference, no speed difference, no lift. Symmetric aerofoils fly magnificently. They generate lift with no problem at all. You simply give them a non-zero angle of attack. Tilt the wing slightly relative to the oncoming air, and up they go. Every single acrobatic aircraft uses symmetric or near-symmetric aerofoils. The theory says they shouldn't work. They work.
Problem 4. Inverted flight. Aerobatic pilots fly upside down regularly. Roll an airplane inverted, and now the curved surface faces downward toward the ground. According to equal transit time, the lift should now push the plane toward the Earth even faster, which would be a bad day for the pilot. What actually happens, the pilot adjusts the angle of attack, and the airplane continues flying just fine. The pilot is not performing a miracle. They are doing something the equal transit theory cannot explain, which is flying in a configuration the theory says should be catastrophic. And, since we are adding embarrassments, a paper airplane. A folded sheet of paper, flat on both sides, no curve anywhere. According to the standard textbook explanation, a paper airplane should be physically incapable of flight. Every child who has ever thrown one across a room has conducted an inadvertent experiment refuting a widely taught scientific claim. The bumblebee tangent. You may have heard that according to physics, a bumblebee cannot fly. People repeat this with great affection. The little bee, thumb on the nose of aerodynamics. Charming story. Here is what actually happened. At some point in the early 20th century, someone applied the lift equations for a rigid fixed wing to a bumblebee and got a number that said the bee could not generate enough lift to stay airborne, which is correct. A bumblebee cannot fly like a fixed-wing aircraft. But a bumblebee is not a fixed-wing aircraft. Its wings flap, they twist, they rotate on each stroke and generate complex leading-edge vortices that a rigid wing analysis is completely blind to. When you apply fluid dynamics appropriate to flapping, rotating, unsteady wing motion, because that is what is actually happening, the bumblebee flies without any theoretical objection whatsoever. The mystery was never in the physics, it was in the mismatch between a real flapping insect and the model someone chose to represent it. Using the wrong model and then declaring that nature has violated the laws of physics is not a discovery. It is a category error. Bernoulli is not the problem. Before moving on, I want to defend Bernoulli, because people sometimes hear that the standard explanation is wrong and conclude that Bernoulli's principle must be the culprit. It is not. Bernoulli's equation is correct. In a flowing fluid, faster-moving regions do have lower pressure. If you know the actual velocity of the air at every point around a wing and you apply Bernoulli, you get the actual pressure at every point. Integrate that pressure distribution and you get the actual lift. It works.
It matches experiments. The problem is not Bernoulli. The problem is that people use the equal transit time assumption to guess the velocity, and that guess is wildly wrong. Feed bad input into a correct equation and you get a wrong answer. That is not the equation's failure. Bernoulli is fine. Equal transit time is the fraud. What is actually happening? Forget everything for a moment. Let's start over from the most basic physical principle there is. Newton's third law. Every action produces an equal and opposite reaction. Push something one way, it pushes you back the opposite way with the same force. Here is a demonstration you can do right now if you are somewhere with a window. Next time you are in a car on a highway, stick your hand out and hold it flat, parallel to the road. Air flows over and under with roughly equal indifference. Not much happens. Now tilt your hand. Just tilt the front of your palm upward 5 or 10 degrees. Immediately, not gradually, immediately, a strong force shoves your hand upward. You have to work to keep it in place. What happened? Your tilted hand is redirecting the airflow. Air that was moving horizontally toward your hand is now leaving your hand, moving partially downward. You pushed the air downward. The air pushed you upward. That exchange of momentum is what lift is at the most fundamental level. A wing pushes air downward, and by Newton's third law, the air pushes the wing upward. This downwash, the column of air behind a wing that is moving more downward than it was before encountering the wing, is real, measurable, and present behind every aircraft in flight. The total downward momentum imparted to the air per second equals the weight of the aircraft. It has to. Conservation of momentum requires it. If you have ever watched a large plane fly low over a lake, the disturbance you sometimes see on the water surface below it, that is the downwash. The angle of attack, the angle between the wing and the oncoming air, controls how much air gets deflected. More angle, more lift, until you reach the limit, which we'll get to shortly. This works for flat plates, for curved wings, for paper airplanes, for your hand. It explains inverted flight. The pilot simply adjusts the angle of attack so the wing still deflects air downward despite being inverted. The Newtonian picture is right, but it is not the whole picture.
Measurements of real wings show something that surprises people. About 2/3 of the total lift force comes from the top surface of the wing, not the bottom. The bottom pushes up, yes, but the top surface, due to a region of low pressure that forms above it, pulls the wing upward even more strongly. To understand why that low pressure forms, we need to understand something strange about air. Air is sticky. I know that sounds wrong. You move through it constantly without noticing resistance, but at the molecular scale, air exhibits a behavior called the no-slip condition, and it is one of the most experimentally well-verified facts in all of fluid dynamics. Right at the surface of any solid object, the air velocity is exactly zero relative to the surface. Not approximately zero, exactly zero. The air molecules touching the wing surface are moving with the wing, not past it. A fraction of a millimeter above the surface, the air is moving slightly. A few millimeters up, it is moving faster. Eventually, some distance from the surface, the air reaches the full velocity of the oncoming flow. This transition zone, from zero velocity at the surface to full free stream velocity some small distance away, is called the boundary layer. On an aircraft wing at cruising speed, this layer is astonishingly thin, a few millimeters near the leading edge, less than a centimeter over most of the wing. You could not see it or feel it. It would not show up if you ran your finger along the wing surface. And yet this invisible sliver of sluggish air is responsible for the existence of flight. Prandtl's 8 pages. In 1904, a young German physicist named Ludwig Prandtl gave a talk at the Third International Congress of Mathematicians in Heidelberg. His written notes ran to 8 pages. The audience did not fully appreciate that they were watching the birth of modern aerodynamics. Before Prandtl, engineers were trapped between 2 unsatisfactory worlds. On one side, elegant mathematical theories of fluid flow that treated air as a perfectly frictionless fluid. These theories were solvable, but they gave absurd predictions. Most famously, they predicted that a body moving through a fluid at constant speed experiences zero resistance. Not approximately zero, exactly zero. We will come back to how embarrassing that is. On the other side, experimental measurements of actual forces on real wings and bodies, with numbers that the frictionless theory could not explain at all. Prandtl's insight was to stop treating the fluid as uniform everywhere. Far from the wing, the frictionless equations work well. Viscosity is negligible there. But very close to the surface, in that thin boundary layer, viscosity dominates everything. And the equations describing that thin layer, while different from the full Navier-Stokes equations, are simpler because the layer is so thin. Solve the boundary layer equations near the surface. Solve the frictionless equations everywhere else. Stitch the 2 solutions together at the edge of the layer, and suddenly, predictions that match reality. 8 pages, a century's worth of confusion resolved. The Kutta condition and the birth of circulation. Here is what the boundary layer actually does to enable lift. Because viscosity forces the air velocity to 0 at the wing surface, the flow near the trailing edge obeys a critical constraint. Air cannot make a sharp turn around the trailing edge from the bottom of the wing to the top. The viscous forces in the boundary layer prevent it. Instead, the flow must leave the wing smoothly at the trailing edge, neither overshooting to the top nor leaving abruptly from the bottom. This is the Kutta condition, named for the German mathematician Wilhelm Kutta. The moment the wing begins moving, say during the takeoff roll, the flow initially tries to wrap around the trailing edge, but it cannot sustain it. The boundary layer causes the flow to separate, and a small spinning vortex peels off the trailing edge and gets left behind in the air. This is the starting vortex. You can watch it form in smoke tunnel experiments, a tiny, persistent swirl marking the moment lift began. Now we invoke a theorem from fluid dynamics, Kelvin's circulation theorem. In an inviscid fluid, the total circulation, a measure of rotational motion, within any closed fluid loop cannot change over time. When the starting vortex is shed with a certain rotational direction, conservation demands an equal and opposite rotation develop somewhere else in the system. This is called the bound circulation. Circulation is a strange concept. It doesn't look like anything. The air is not visibly spinning around the wing like water down a drain. What it means mathematically is this. If you trace a closed loop through the air surrounding the wing and add up the component of air velocity at every point along that path, you get a non-zero result. There is a net swirl in the velocity field, invisible but real and measurable. And this circulation is directly and exactly tied to lift through one of the most beautiful results in all of fluid mechanics, the Kelvin-Joukowski theorem, developed independently by Wilhelm Kutta and the Russian physicist Nikolai Joukowski in the early 20th century. The lift per unit length of the wing is equal to the fluid density multiplied by the free stream velocity multiplied by the circulation. 3 numbers, multiply them together, that's your lift force. It doesn't matter what shape the airfoil is. It doesn't matter whether it's thick or thin, cambered or symmetric. If you know the circulation, you know the lift. The full causal chain looks like this. The wing moves through air. Viscosity enforces the no-slip condition.
The Kutta condition requires smooth flow departure at the trailing edge. A starting vortex is shed. Kelvin's theorem requires equal and opposite bound circulation to form around the wing. That circulation produces a velocity distribution. Air moves faster above the wing, slower below. Bernoulli's equation, applied to these real velocities, gives you the actual pressure distribution. That pressure distribution, low above, higher below, integrates to give you lift. And the whole system produces a downwash behind the wing, consistent with Newton's third law. Every step follows from verified physics. No equal transit time, no magical air reunions, just viscosity, conservation laws, and differential equations.
The most embarrassing result in physics. Allow me to take you back to 1752 and introduce you to an exceptionally talented mathematician named Jean-Laurent d'Alembert. D'Alembert was not a minor figure. He was one of the editors of the Encyclopedia, the great intellectual monument of the French Enlightenment. He was a serious physicist and a superb mathematician. He posed a simple question: what net force does a fluid exert on a solid body moving through it at constant velocity? He wrote down the best equations available: incompressible, inviscid, potential flow, a mathematically perfect frictionless fluid, carried out the calculation correctly, and got an answer. 0. Not the lift, not just drag, everything. 0 net force in any direction. In a perfectly frictionless fluid, an object moving at constant speed through that fluid feels nothing. The fluid parts in front of the body, flows symmetrically around it, closes behind it, and the pressure pushing forward at the back exactly cancels the pressure pushing backward at the front. D'Alembert knew this was absurd. Ships obviously slow down in water. Arrows decelerate in flight. He published the result with unusual intellectual honesty, acknowledged it made no physical sense, and asked future mathematicians to figure out what he had missed. It took about 150 years. The puzzle that kept brilliant people occupied for a century and a half was not just that the answer was wrong, it was the nature of the wrongness. Real air has very low viscosity. It feels almost frictionless. Surely a theory that models air as perfectly frictionless should at least approximately describe reality. 0 is not an approximation. It is not in the right neighborhood. How can removing a tiny amount of viscosity completely destroy your answer? Prandtl's boundary layer is the answer. No matter how small the viscosity, it creates a boundary layer where its effects are concentrated. And that boundary layer, however thin, changes the character of the entire flow in ways that the frictionless model cannot capture. The no-slip condition introduces asymmetry. It allows the flow to separate. It permits the Kutta condition to operate. Remove viscosity entirely, even infinitesimally, and all of this evaporates. Mathematicians call this a singular perturbation. The solution to the equations at 0 viscosity is not the smooth limit of the solution at very small viscosity. It is a fundamentally different solution. You cannot approach frictionless flow by making the fluid less and less viscous and expect a gradual transition. At some point, the qualitative character of the solution changes abruptly. The frictionless limit is a cliff, not a ramp. And here is what I find genuinely breathtaking about this. In a perfectly frictionless universe, there is no lift, none. The most mathematically clean, idealized version of fluid flow predicts that wings do nothing. Airplanes cannot take off. The atmosphere is aerodynamically inert. What saves flight from this mathematical prison is friction.
Viscosity, the very thing that creates drag, that burns extra fuel, that engineers spend decades trying to minimize, is also the only reason lift exists at all. The same property of air that works against flight at every moment is the reason flight is physically possible in the first place. The enemy is the prerequisite. I am not sure I know a better example of irony in all of physics. So, do we know why planes fly or not? You may have encountered the claim, according to physics, planes should not be able to fly, and nobody fully understands why they do. The first half has a kernel, a very small kernel of truth. In D'Alembert's frictionless mathematical model, flight is indeed impossible. But using this to suggest real flight is mysterious is like saying cars should not move because you built a model that forgot about friction between tires and road. The model was incomplete. Real physics, with viscosity included, predicts lift accurately and reliably. There is no paradox in actual fluid dynamics. The second half, nobody knows why, is more interesting, and it points to a real open problem, just not the one people think. The equations that describe fluid flow, the Navier-Stokes equations, first written by Claude-Louis Navier in 1822 and refined by George Gabriel Stokes, are almost certainly correct and complete as a description of how ordinary fluids behave. We use them constantly. Every commercial aircraft designed in the last 50 years was built using computational solutions to these equations. They predict aerodynamic forces with extraordinary precision. If we didn't know how flight worked, airlines would not exist. But here is the genuine mathematical mystery. The Navier-Stokes equations are nonlinear. The velocity of the fluid at any point depends on velocities at neighboring points, which depend on their neighbors, and the mutual dependencies do not decouple neatly. For most real cases, we cannot solve the equations analytically in closed form with a nice formula. We solve them numerically, divide space into millions of tiny cells, step forward in time, compute approximate solutions, and this works extraordinarily well in practice. But what nobody has proved is whether smooth solutions to the three-dimensional Navier-Stokes equations always exist, or whether they can develop singularities, points in space and time where the mathematical solution blows up to infinity. No simulation has ever produced such a singularity. No experiment has ever suggested one, but no one has proved they cannot occur. This problem, the existence and smoothness of solutions to the Navier-Stokes equations, is one of the 7 Millennium Prize problems identified by the Clay Mathematics Institute in 2000. There's an unclaimed $1 million prize waiting for whoever resolves it. It's widely regarded as one of the hardest open questions in mathematics. But this is a mathematical question, not a physical one. Saying it means we don't understand flight is like saying we don't understand arithmetic because of Gödel's incompleteness theorems. The incompleteness theorems are real and important and fascinating, and they have approximately nothing to do with whether 2 + 2 = 4.
One more confusion worth clearing up. You will hear people argue about whether lift is explained by Newtonian momentum exchange or by Bernoulli pressure differences, as if they represent competing camps and you must pledge allegiance to one. They are not competing. They are the same phenomenon viewed through different lenses. Saying lift comes from deflecting air downward is describing the net momentum exchange between the wing and the air. Saying lift comes from a pressure difference between the top and bottom of the wing is describing the local force distribution on the wing surface.
Saying lift comes from bound circulation using the Kutta-Joukowski theorem is describing the mathematical structure of the velocity field. These three statements are not in conflict. They are different sentences about the same physical reality, like describing the same room by its color, its dimensions, and its temperature. All three are true. None of them is complete on its own. Together, they tell you the whole story. The only problem arises when someone takes the Bernoulli route and then contaminates it with the equal transit time assumption to estimate the velocity. Bernoulli is not at fault for that. Any correct tool will give you the wrong answer if you feed it wrong inputs. So why the wrong explanation won't die? Why will a random high school physics teacher with every good intention probably explain lift incorrectly tomorrow morning? Two reasons. First, the wrong explanation is easy to teach. It fits on a slide. It takes 3 minutes to explain. It has clean visual logic. The correct explanation involves boundary layers, the no-slip condition, the Kutta condition, starting vortices, Kelvin's theorem, and bound circulation. That takes longer, requires more conceptual scaffolding, and is harder to draw on a whiteboard. In an educational system that rewards brevity, the simpler wrong answer beats the more complex right one. Second, once a wrong idea enters the textbook ecosystem, it becomes nearly impossible to dislodge. A teacher who learned it from their textbook teaches it to students. Those students become teachers. They pass it on. Each person in the chain believes they're transmitting accurate knowledge. They are not lying or being careless. They are faithfully teaching what they were taught. The error replicates generation after generation. NASA has published explicit corrections on their educational website explaining in detail why equal transit time is wrong and what actually generates lift. And yet, if you surveyed physics classrooms tomorrow, a significant fraction would still be teaching the old explanation. This is one of the more insidious failure modes in science education. Ignorance is easily fixed. You just supply the missing knowledge. But confident wrongness is a much harder problem. Before you can teach someone the correct idea, you have to first dislodge the incorrect one they already have, which requires them to accept that something they were taught, tested on, and perhaps taught to others was false. That feels like an attack. People resist it. This is not unique to aerodynamics. Electrons do not orbit atomic nuclei like tiny planets. Light does not decide to be a wave or a particle, depending on what you measure. Gravity is not a force pulling objects together. It is a curvature in space-time through which objects move along the straightest possible paths. Every one of these is a simplified model that was useful at one stage of understanding and then calcified into dogma that resists correction. The map is not the territory. The model is not the phenomenon. And the moment you forget which one you're looking at is the moment you stop learning. The moment it all clicks into place. If you ever watch a wind tunnel test, even a good computational simulation on a screen, there is a particular moment I want you to notice. The instant the flow is switched on and encounters the wing, there is a brief chaotic scramble at the tail edge. The air does not know what to do yet. For a fraction of a second, it tries to curl around the sharp edge, fighting against itself. Then the starting vortex peels away and drifts downstream. You can see it roll off and fade. And in that same instant, as if something clicked into place, the flow over the wing snaps into its steady pattern. Smooth, attached flow above. The pressure distribution locks in. The downwash appears behind the wing. And that's it. The wing is flying. This happens at the start of every single flight, at every airport, on every runway, thousands of times a day around the world. A starting vortex is born, drifts away, and several 100,000 pounds stay in the air because of the invisible mathematical consequence of its departure. D'Alembert showed us what a frictionless universe would look like, and it's strangely dead. No drag, yes, but no lift either. No interesting fluid behavior of any kind. Air slides past everything with mathematical perfection and produces nothing. No weather systems, no ocean currents, no spiraling smoke from a match, no wake behind a boat. Perfect frictionless flow is a universe where fluids exist but do nothing. Beautiful on paper and completely inert. The real universe has viscosity. It has boundary layers and turbulence and starting vortices and the gorgeous chaotic complexity of separated flow at high angles of attack. It's harder to calculate. It's much harder to prove theorems about. But it's the universe where a thin coat of sluggish molecules clinging to a metal surface can cascade through a chain of physical consequences into several hundred tons, staying airborne for 16 hours between continents. The deviations from the clean mathematical ideal, the places where reality refuses to be as simple as the frictionless model, are not failures of the physics. They are where the interesting physics lives. Flight does not succeed because of the messiness of the real world. It succeeds because of it. Next time you're in a window seat and you look out at that wing, slicing through the air at 400 miles per hour, maybe 30 kilometers above the ocean, remember this. It's not flying because the air on top has to run a longer race. It's flying because air molecules are sticky enough to drag each other, because a thin, invisible skin of slow-moving air clings to the metal surface, because this forces the tail edge to shed a tiny vortex the moment the aircraft begins to roll, because that departing vortex summons its mathematical equal and opposite in the airflow around the wing, because this circulation produces a genuine pressure difference, and this pressure difference, summed over every square inch of wing surface, adds up to a force large enough to lift a machine the weight of a small building clear off the ground. No one commanded the air to do any of that. It follows from the physics automatically, inevitably, every single time. That's not a mystery, that's understanding. And understanding this, actually understanding it, rather than carrying around a pleasing fiction about paths and races, is worth something. So here's a question to leave you with. What other explanation are you carrying right now that you learned, accepted, and never once checked?